All right, hey guys, welcome back to Full Metal Scientist. I'm actually doing this interview style video for the first time. So I'm at a conference right now in Pittsburgh, and I'm here with my buddy Braden Li. He is a PhD student in was it textiles?
Yep.
Text
Fiber and polymer science.
Fiber
Yeah.
and polymer science.
hmm
Okay, so stuff I don't really understand, but you guys will learn a little bit more about it today. So just to introduce him a little bit, he also won the SMART scholarship offered by the Department of Defense. So
Thank
congrats.
you. Thank you, fam.
But
Appreciate it.
yeah, I'm here to kind of learn a little bit more about smart textiles, and since we're sort of at a leadership conference, maybe kind of talk about the merits of strong leadership in academia, but also just doing graduate work. So yeah, I'm excited to be here.
Me too.
Do
Yeah.
you this actually I don't remember. Is this your
It's my
third
third
con?
one. Third one. Yeah. Because I was back here in 2016, and then last year 2018, and then now, so 2019.
Okay, so yeah, it's my sixth conference here.
Sixth
So
conference.
yeah,
You've been
it's
involved with space for a long time, huh?
yeah, I'm getting old here.
We're all old now.
But yeah, tell us a little bit more about your work on textiles
Yeah,
and
yeah.
kind of what you do in the space and sort of how you got started.
Yeah, yeah. Well, first off, thanks for having me.
Yeah.
So really appreciate it. Have you done like a polymers kind of lesson or talk yet? Or
No, actually. So
so
this is
I
this
guess
is all gonna be new.
I guess I can like start from there, right?
Yeah.
Because so all textiles are made from polymers, and polymers can either be synthetic or natural. So they can be derived naturally from cotton, or flax, or what's another one, bamboo. And then you can go to the more synthetic route, like polyester. Oh, wool's another natural one. That's a big one. But polyester is a synthetic, nylon, rayon, spandex. That's when we start getting more synthetic fabrics. But it all starts from the polymer level. And polymers are unique because I'm a big fan of them because like they're always like I think they vibrate more right than metals.
Hmm.
They're always like constantly moving, so they exhibit what's called viscoelastic behavior. So basically, one part of the polymer is viscous and the other part is elastic. So meaning one part likes to move and the other part doesn't. So depending how much force you apply is when they start to act. All those chains within that polymer system will start to kind of move around. So from a textile perspective, like when you're making these fibers, you have to really consider how that structure interacts with um, your manufacturing technique. But yeah, I think that's a good base lesson for polymers, right? Viscoelasticity,
Yeah.
polymers. So poly means many, mers mean parts. So polymers are made up of a lot of different monomers. Um, and we combine all those monomers, you get a polymer.
Yeah.
And then you have different repeat units. So you actually take this very, very long spaghetti chain, you can imagine, and then split it into different components. And you can see that it's a periodic repeating structure. Like, oh, you know polymers too. So
Yeah. A little bit, but not as much as you.
uh,
Yeah.
I'm like I say I have a background in polymers, but like I don't know if I
Yeah.
do. Yeah.
Actually, what is your background again? I know like we're both
Yeah.
material students, but did you
hmm
like have a specific focus
Yeah,
back
yeah.
then when you were still an undergrad?
So back at my undergrad at UF, I was focusing on polymers and biomaterials, and actually my uh, undergraduate thesis project was focused on making biodegradable fibers for
Oh,
drug delivery.
that's awesome.
So I was looking a lot at trying to manipulate that chain structure I was talking about earlier. But instead, so we would use polyethylene oxide, polyethylene glycol,
Hmm.
um, and basically the two the hydroxyl groups on either end, we would functionalize the middle and add an acrylate. And then the acrylate can actually be cleaved off by a specific enzyme. So we were trying to like create enzymatically degradable fibers.
Oh, wow.
Yeah, and then I was loading them with different drugs and then trying to see if I can get it to release that drug. So,
Yeah. So as an undergrad, I did not necessarily something similar, but we were trying to like have a long-term goal of making antimicrobial surfaces. So
mm,
we actually studied functionalization of fullerenes. So fullerene is basically like a soccer ball-like nanomaterial. So it's carbon 60, and we were trying to make it more water soluble by adding hydroxyl groups or OH groups
mm,
onto the
mhm,
surface.
mhm,
And the idea was to try to get them to self-assemble on a surface, effectively coating the surface, but also to exploit its antimicrobial properties. So there were people that actually worked on creating uh, sort of bacteria-resistant surfaces,
Hmm.
and this kind of was the inspiration for that work. It didn't go anywhere because I didn't know what I was doing as an undergrad, and even just a simple act of replicating papers was also a bit of a challenge.
It's
So,
always tough.
um, so yeah, I thought that was kind of a cool little application
Hmm.
there. Um, but so we both just came from this SASE talk type event, so kind of an open forum discussion, 15 minutes. We just talk about whatever we feel like in this professional conference setting. But you just actually had a talk on smart textiles and sort of the
Mm-hmm.
paper that you just published. So
Yeah.
could you give us a brief overview as to what kind of
Hmm.
materials you were working on for that paper
Yeah,
specifically?
yeah. So like kind of going back to the polymer perspective is that polymers inherently are not electrically conductive. So like I know with a lot of materials you work with, they're very conductive.
Yeah.
Polymers behave as insulators. So what we try to do in our lab is try to add electronic functionality, make our polymers conductive, but we don't necessarily modify it on the polymer scale. We modify it more on the macro scale. So stuff you can see. So like, for example, we take the jacket I'm wearing or the shirt I'm wearing, and then we print conductive materials onto the textile. There's a lot of different ways you can go about it. There's the most common way in the textile industry is actually screen printing. So like most t-shirts have a screen printed design. It's a very thick viscous ink, think thicker than honey. And what you do is you have this screen that filters out um, your, uh, your 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 metallic particles, your conductive
Mm,
particles within a ink, and then create a nice smooth layer on whatever you're printing on. In this case, it'd be a textile. But the drawback with screen printing is that it creates a very thick layer on your textile. So it doesn't feel like a textile when you screen print a conductive material on there.
mm,
Because like most screen printed designs are like the polymer, it is viscous but still pretty light, so like you don't feel it as much.
mm.
But when you print these conductive materials, you have to have that electrical percolation, so they gotta be really close. So all the pores in your shirt are gone. It's
Right,
not breathable anymore.
right.
Then you have problems of durability and washability, which is what I know I talked about a little bit earlier with the durability aspect. But washability is a big thing because you have to encase your silver, and
Of
because it's
course.
it's kind of like just a top layer on your textile. It's not necessarily inside your textile. It's just gonna want to flake off
Right.
because energetically it's just gonna want to pop off. So, but the other method, what we use in our lab, what we like to use now is inkjet printing. So think of inkjet printers like in your office or in your home.
Hmm.
Um, you probably have one in your home that prints ink onto paper. So like when you go get stuff from your office printer, it's usually an inkjet printer or a laser printer, but or laser inkjet printer. Still inkjet either way.
Yeah.
And basically all it is you have a really really tiny nozzle. So think of 20 micron in diameter.
Okay.
So how thick is hair? Like 100 microns, right?
I actually
I
don't
think
remember.
I think it's like 100 microns.
Yeah.
So it's 5 times smaller than the diameter of hair. So it's
Yeah.
very hard. You basically can't see these nozzle sizes.
Right.
Um, but since they're so small, you can create really fine patterns on textiles. And we also kind of play a little bit with the material science and the chemistry.
Hmm.
We employ what's called organo metallic inks. And basically, the system we use has silver in it.
Hmm.
And you have this silver ion that's surrounded by organic ligands.
Hmm.
And then when you apply heat, what happens is these organic ligands want to detach from that silver,
Hmm.
and then they will just burn off into ammonia and like water and CO2. So then all you're left with is silver.
Hmm.
And what's really cool about the fluid properties of these inks is that it behaves like water.
Hmm.
So think of as I'm sweating, the sweat wants to wick through my shirt.
Hmm.
We use the same properties here on the textile. So when we print, instead of just having a top conductive layer, now we have a conductive layer throughout the material
Hmm.
that's a little bit more consistent. Not only that, but the coating is super thin,
Hmm.
but thin enough to get really good conductivity for like e-textile and smart textile applications. So you don't interfere with the feel of your textile, so it still feels like a shirt,
Hmm.
which is really cool. And that's what one of my colleagues in my lab had published first in Won Kim, Advanced Functional Materials 2018. Just go
Ah.
look for it. probably like link here, right? Something like that when
Yeah.
you post it.
I'll put something down
Paper
here.
here.
Yeah.
But then the paper I published, also paper here, um, was taking that technique, but then expanding it further and being like, well, how can I improve the reliability and the durability of our inkjet printed devices?
Hmm.
So I'm very inspired by the art of Kirigami, which I've told Wilson like 1,000 times. Uh, but Kirigami is basically the art of Japanese paper cutting. Actually, I'll go a little bit more into detail now compared to my talk earlier.
Right.
With these cuts, think of a 3D pop-up book.
Yeah.
Paper in itself should not be able to pop up in your face.
Mm-hmm.
But when you cut in a very periodic manner, you're able to get that paper to basically deform out in a three-dimensional plane. So instead of a 2D plane, it's coming up to you.
Yeah.
But it turns out you can apply that to any material class. Whether I don't think they've done it on ceramics yet, but they've done it on metals.
Mm-hmm.
They've definitely done it on like all sorts of polymers.
Yes.
But they haven't done it on textiles because inherently textiles are very stretchable.
Yes.
And you wouldn't necessarily need to increase the stretchability or the deformation of a textile. But in the case of e-textiles, let's say if I'm trying to make a circuit on my textile, because that's what e-textiles are, right? You're trying to make a circuit on a textile, route electronics like a conventional computer or any other device you would find, consumer electronic. The problem is that we have to now tackle the textile properties, which it is stretchable. Now we have very hard materials. So what happens at the hard and soft interface? It wants to break, right? Because that interfacially, it just the elastic moduli don't match. So then we start stretching or folding, it just wants to fail.
Yeah.
So with Kirigami, if you cut it in a very periodic manner, you're actually able to control the stresses in certain regions, which allows for that relaxation to basically pop up in the third dimension, which is why that 3D pop-up book effect. So that's what my paper was exploring, was taking a center cut Kirigami design that was previously done by a group out of Michigan, and they published in Nature Materials. Paper here if you want to post that later, but
yeah.
their work is awesome. And a couple other research groups out of Harvard too have really studied these Kirigami designs. So I was like, well, why not just apply it on a textile and see what kind of cool properties we can get. As a matter of fact, we're able to get the same mechanical properties as other people were reporting. But if we look now at the electrical and mechanical properties, we combine them. You can call that, we refer to, and a lot of people in this field refer to electromechanical coupling.
Right.
We're actually, that relates to your durability of your device. So we're actually able to increase the durability of your device. And more interestingly, we're actually able to increase the conductivity upon stretching, because conventionally, what's the equation? You have physics 101, resistance is equal to resistivity times length over your cross-sectional area.
Yes.
Right? So you can think of your length over area as like a dimension, as a geometric parameter. And as you stretch your material, I am increasing the length while also decreasing the cross-sectional area. But usually that leads to an increase in resistance.
Yes.
Which leads to a decrease in conductivity. In our case, we show a decrease in resistance, which means we're increasing conductivity. And this is because the textile we're using is a knit textile. So it has all these loops that kind of interlace with each other. And as we stretch that textile, the loops want to make more contact. And since we're using inkjet printing, all the conformal layers are making more contact with each other. So think of, like, I like to use an analogy, think of a river. And the river is kind of like your resistance, but then all the water in that river are your electrons.
Right.
So that's what transmits electricity or electrons. And as we stretch a conventional material, that river kind of gets narrower and narrower and narrower and narrower and narrower. And what happens is, if I'm still trying to flow the same amount of electrons, it takes more work for me to push those electrons from point A to point B.
Yeah.
But now, if I start making more connections, although even though I'm narrowing that river, think of more streams kind of coming in. So it's still able to help that flow of electrons to move through. So now, from point A to point B, I'm actually opening up more conductive pathways as opposed to closing them off.
Yeah. And that's a good way to put it, because the way I was kind of seeing it in my head is that, like by making all these extra percolating networks, you're
Mhm.
still effectively increasing the total length of your travel pathway, so that you're still I guess either maintaining or lowering that total
Mhm.
resistance
Mhm.
in that sense. But I think that was a really good analogy, and something I actually want to talk about, because you brought up the idea of organometallics, and
Mhm.
to my sort of limited knowledge in this area, like those materials are typically toxic.
Yes.
So how do you guys deal with
Mhm.
handling those types of materials, and like when you burn off these organic layers to leave behind the
Mhm.
metal onto the fabrics, like what do you guys do in terms of safety and precautions or things like
Mhm.
that?
So actually, the system we chose in particular, the organic compounds, they're not super volatile. They are, but they don't burn off into anything toxic.
Mm.
So, and also I forget what solvent, because we purchased inks from a company.
Hmm.
Um, I don't know what solvent they use. I'm not gonna mention the company because it's proprietary
Right, right,
information. But
of course.
um, the solvents they use, I believe, are non-toxic, because the ventilation we use for our printing system, there is no ventilation. So it's basically we're like breathing in whatever's burning off, but what is being burned off is only ammonia, CO2, and water.
Only ammonia.
Yeah, I mean, but you'll be okay, right? Just don't breathe too much of
Yeah, it's
it.
okay. I've worked with ammonia before. It doesn't smell that great anyway.
Yeah, I mean, it's a common household cleaning product,
Yeah,
right? So it shouldn't affect you. I mean, obviously, anything at high enough doses will mess you up. So be careful with ammonia.
yeah.
Shouts to ammonia. But yeah, it's not in such high concentrations. I think like I don't know what's the parts per million, but it's not enough to be toxic levels when you bring
Yeah.
that in. But yeah, to your point, you want to make sure we cure it at such a temperature where we're burning off all the organics, so there's nothing left, and we're also making sure that it doesn't interfere with the textile either. So the temperature we cure at is it's in the paper as well. Um, it's like 135 degrees Celsius,
Okay.
which is since the textile we're using 100% polyester, that's way below the TG of 165
Mm.
degrees C. So we're good there. Yeah.
Okay.
So it doesn't really interfere with the properties of the textile either. So,
Yeah, and I think TG he just referred to as glass
but
transition.
that's right. Yeah, the glass
So
transition. Yeah.
basically, how a polymer goes from very stretchy to
Hmm.
more compact and brittle.
Hmm.
Um, but yeah, this is interesting. I'm sort of looking forward to seeing where this goes. And
Yeah.
in your opinion, like what do you think is the main hot topic in stretchables, or what's the future in this field
I,
like?
so in particular with e-textiles, a lot of work has been done in one trying to get these materials onto a textile and studying those interactions. But I think the main which is what our lab focuses on is developing the systems. So you have to consider routing the electronics, the sensors, how are you going to power those sensors, what are those sensors going to communicate to. Um, I think, my opinion, a lot of work has also been done that, but I like to see more like actuation, like soft actuation
Uh,
of materials. So like
right.
a lot of stuff has been done with PDMS, which is polydimethyl siloxane.
Mhm.
So it's think of it like it's like a silicone material. It's pretty sticky.
Yeah,
Um,
pretty
a-
common polymer everyone
yeah,
uses.
but it's not in consumer products.
Yeah, it's actually there's like a worldwide shortage of that apparently,
Is
right?
it? I believe it.
Yeah, I think so. Uh,
I didn't know that.
yeah,
That's crazy.
it's kind of weird because like it's a polymer that everyone kind of uses in their
So
work.
like everybody researches it, but it's not in like any consumer products, which is wild, right?
Yeah,
So all these papers that come out, it's all focused on PDMS, but
right.
I haven't seen too many papers on actuation of textiles. Like, wouldn't it be great if you just put on a textile, whatever size it was, and it just fits you automatically?
Yeah,
That would be really cool. And that's
self-lacing shoes, but for
self-lacing
your
shoes,
body.
Back to the Future. Yeah, so Marty McFly, hey Doc Brown, let me get those shoes. You know, he puts them on, self-laces, but imagine
Yeah.
that for your shirt.
Actually, I think Nike a couple like was it this year or last year they actually had like a prototype for
I think so.
self-lacing shoes.
A lot of Nike. So Nike came out with one, the
Yeah, yeah,
Nike Hyper Adapt. Yeah, and they actually gave a pair to Marty McFly. And it's all over social media of
yeah.
him using it and stuff. It was really cool. But to the self-fitting garment aspect, research has been done on. There's these machines called whole garment knitting.
Uh-huh.
I don't know if no, we're not wearing any knitted. Well, this is kind of like the shirts we're wearing are kind of knitted.
Yeah.
But they're cut and sewn, so there's like different pants. So you can see, I don't know if you can see that seam there, right?
Yeah.
And even on my suit, there's different seams.
Yeah. Like
Whole,
different kind of sections here.
yeah. So with whole garment knitting, you actually don't have, it's seamless. Everything is sewn directly on that machine, and it's flatbed. So when it comes off, it looks like a sweatshirt. And what people have been working with is going back to the origami kirigami thing, is trying to manipulate that structure in a three-dimensional way. So when it comes off the knitting machine, all you have to do is put on the shirt. And I think they put in some like other heat reactive materials in there. So when you apply, you literally take an air dryer and you apply heat to it, it wants to conform back
Oh, so
to the
kind of
user.
like that shape memory alloy stuff that I
Yes.
mentioned earlier.
Yeah, there's also a really interesting paper that was actually just published, I think, in the same issue as mine, in Advanced Materials Technologies, and they look at nickel shape memory alloys,
Yeah,
but
so
for what I was saying, for self-fitting garments.
mm,
But the problem with that is shape memory alloys, as you know, are very expensive.
yeah.
Yeah, and putting it into a textile is not feasible because, just for example, like a typical, maybe like the shirt I'm wearing right now,
Yeah.
medium size, you would need at least yarn wise, if you were to knit it on a whole garment machine, for example, you would need at least over 1,700 yards of yarn.
Mm,
And I kid you not, that's what I remember looking at the
yeah.
machine, and like there's this company called Shimaseki that like our college works with.
Yeah.
And it tells you on the machine like how much yarn you need.
Yeah.
And like 1,700 yards. I was like, that is crazy. Can you imagine trying to like that's a lot.
Yeah.
That's a lot.
Try to manufacture that
That's
much
17. That's over 17 football fields long. Yeah.
Wow.
So, but fibers, yarns are like pretty small in diameter, but still, it's a lot of freaking yarn. So,
Yeah.
I can't imagine how much that would cost for shape memory alloys. So yeah, going back to the future of the space is trying to make how can we take manufacturing methods that are used in the textile industry and merge it with an electronics industry and kind of find a happy medium where the price point can meet the consumer satisfaction.
Yeah.
But also, can we create materials that are cheaper to produce, can be mass produced for something like a textile platform? Yeah. So
Yeah.
it's always like it's a very conflicting field because
Yeah, and the thing is, that's how it is with these types of technologies, where it's
Mhm.
like a lot of the driving factors are not necessarily the research innovations, but really cost of
Yeah.
processing,
Mhm.
and also like even the ease of manufacturing the material as well. So,
Yeah,
um,
which is a shame because there's a lot of great applications like e-textiles and smart textiles can
yeah,
address. Like one I think I was talking about earlier during my talk is like having a garment that can sense your full uh, electrocardiogram, your heart waveform, which can give you diagnosis on like heart murmurs, uh, heart arrhythmias, if you're about to have a heart attack. But a lot of stuff needs to go into that, right? So like the sensors, the other electronics that talk to the sensors, the antennas that communicate out that information, all that good stuff. So yeah.
yeah, and I mean, wearables are starting to become more of a thing. Like we all kind of wear Apple Watches
Well,
and
I don't have
smart
one.
watches.
I got a Garmin, so.
He's got a Garmin. Little pricier, I would think, right?
No, this is not a. It doesn't have any sensors. This is an old school one. It's
Oh.
just a straight running watch. Yeah.
Ah,
Yeah,
okay.
see, yeah.
Never mind then.
Shouts to Garmin. Garmin, if you can sponsor me, this is a.
Yeah.
I love this series. The
It's okay.
Forerunner.
He's already been sponsored.
You sponsor me again. I love the Forerunner. Actually, you know what? I'm not gonna give them any more shouts because like they're
Yeah.
not gonna sponsor me.
I was actually thinking of getting a Garmin myself because like I've stuck with the Apple Watch for now, but like they have really nice GPS trackers on the Garmin
Yes. No,
watches.
I think the GPS tracker on Garmin's are hands down
I don't
the
know
best.
if Matt has any, to be honest, but
Mm.
but yeah, it's pretty cool. Like wearables is definitely an emerging space, and I think that there's so much potential for that in the next 5 to 10 years.
Yeah.
So one thing I want to ask again, like before signing off, is so we are at the Society of Asian Scientists and Engineering conference, so SASE conference, and the purpose is to try to develop young leaders and professionals and who have an Asian American background, but of course it's still open to pretty much anyone who wants to get leadership development. And we were talking a little earlier about sort of the space of people going to graduate school or going and starting their professional careers in sort of the role of leadership. So like I guess what made you decide to like get involved with SASE, and what
Hmm.
were you hoping to get out of it in
Yeah.
terms of either professional or leadership
Hmm.
development?
It's actually it's a funny story. So I knew about SACE in my undergrad. Shouts to the University of Florida. Love my alma mater. Go Gators. Um, my 5th year in undergrad was when I went to my first national conference, 2016 in Dallas. That was like the only time I was really involved with SACE. Like freshman year, I heard about them. I wasn't super involved with them. I was really busy because I was also manager with the track and cross country team, so I took up basically all my time. So I'd be like manager, go to class, come home, maybe try to get my run in, get my workout in,
Yeah.
and then study. So I had like no time for any other clubs, which honestly, looking back on it, I really regret because going to that national conference, what stood out to me more than anything was the networking. And I was just like, wow, there's so many Asian Americans that are trying to do the same thing as me. And growing up, I grew up in Miami, Florida. Just a little background about myself. There weren't a lot of Asian people there, which was kind of tough because I didn't really have. I had my family, but like friends wise, like they didn't understand like the little subtle things, right? So like, I don't know for people watching this video, subtle Asian traits. If you follow that, it's basically a Facebook group, and they post these memes,
It's
but
mostly memes.
it's mostly memes.
Some political stuff, but mostly
It's
memes.
mostly memes, but it's very like subtle Asian things. Like I can't make jokes about rice to my Hispanic friends; they won't get that, right?
Yeah.
I can't make jokes about like, oh yeah, like I got like a 98 on my math exam, and my parents are mad.
Yeah.
Like they won't understand that.
Disappointed.
Yeah, yeah, so disappointed, so disappointed. But they won't get that, and where was I going with this? Yeah, and then going to the national conference, being able to be around that environment with people very similar around me was quite amazing. And now 3 years later, all those people I met at the national conference who were still finishing up their undergrad are now working full time and are now back at this national conference recruiting for their respective companies, which is blows my mind of how deep this network runs in SACE because I go to people. I'm like, "Yo, what's up, Amy? How's it going? Joseph, how's it going? I saw Tien. He works at Procter and Gamble. He's here. I think Fat Lee from
Yeah.
Shell. He's gonna be here.
Yeah.
Allison Mack, I think, also works for Shell now. Amy works for Shell. Annie Dang, she's here. She works for Uber.
Yeah.
These are all the people I met during my undergrad, and now they're working full time.
Yeah.
So it's like, hey, if I need something, I can always go to them for advice, and they can, maybe put me in contact with the right person.
Yeah.
Um, but yeah, after I finished my undergrad, I told myself I need to get involved with SACE in my graduate career. So as soon as I started my PhD at NC State in the fall of 2017, was when I reached out to the SACE chapter there, got involved, and then 2018 is when I became the president of the chapter there,
Mm-hmm.
and then now I'm stepping down, handing it over to the next prez
Mm.
because grad school is busy, PhD life is busy.
Yep.
I feel like 1 year is enough as president, right? I think
Yeah.
it's good to like kind of change it out, let the new kids kind of come in
Yeah,
and take
and just
over.
give like other people opportunities to like kind of develop on their own.
Yeah, and then my selling point to a lot of people at SACE at NC State, at least for me, because I feel like I'm a little bit older now. I tell them, hey, I have the experience. Like you should go to national conference. It's great for getting jobs, but I try to serve as a role model to them as well, which I really like pride myself on because I like to use myself as a resource. I've had internships.
Yeah.
I did research in undergrad. Now I'm a grad student. Um, and just a lot of stuff to share. So for me, SACE is always about giving back to the younger generation because I wish I had a role model that kind of looked like me, or at least culturally was similar to me,
Yeah.
where I could be like, that guy's cool. I want to be like him. And I feel like within our field, there's not a lot of people that we can really kind of lean on and be like, I want to be like him, or like that's super popular,
Yeah.
So
And the thing is, like,
Mhm.
a lot of like Asian Americans are stereotyped as they're going into these types of STEM fields. So like,
Mm.
obviously, both he and I are doing like STEM related
Yes,
work.
we are fitting the stereotype.
Yeah, so we're fitting the stereotype, but like we also want to show that there's definitely a lot more
Mm.
than meets the eye, and
Mhm.
that we have a lot of other potential that we can show. And
Mhm.
doing like conferences like this, like I only met this guy like last year.
Last year, yeah,
Now
last year.
he's popping into this video,
Yeah.
so like yeah, it's great. I love the networking aspect of it, and
Mhm.
hope to come again in the future. But yeah, I think that um,
So
there,
like, why did you get involved with SASE? Like, I think you could talk a little bit about that too. Yeah.
yeah, I actually heard about as you know, I go to Arizona State University, and I actually heard about this from the chapter president from that chapter, and he just started that chapter at the time.
Oh, okay, okay, okay.
I was in my 5th year or going into my 5th year, and I'm like, um, I kind of want to go out with a bang, so let's start a chapter.
Oh, how
So
funny.
so yeah, we started the University of Arizona chapter, and it was a heck of an experience. Like
Yeah.
I reached out to a bunch of people on Facebook that I didn't know, just a bunch of Asian kids on campus, and said, hey, and this is in the days before like instant messenger on Facebook or like groups or anything
Right,
like
right,
that.
right.
I just like found people on the university, and then
That's
they
cool.
became my first e-board. So like
Wow, look at that.
we all kind of bonded through this whole like shared
Yeah.
experience here, and then I wanted to keep involved, so like I started volunteering for the org as like
Mm,
a regional coordinator, and then now I serve actually as a leadership committee chair. So we're trying to work on leadership development
mm,
programs that benefit not only college students but hopefully young professionals as well.
yeah.
So it means a lot to me to like come to these conferences and see like a bunch of familiar faces,
Mm,
and to know that like hopefully doing things that will benefit other people, but
yes,
also
yes.
um, mostly just trying to find ways to benefit myself and
Yeah.
like develop as an individual. So it carries a lot over to my research and academic world, but I think that kind of just making connections like this
Mm-hmm.
and kind of getting to know more researchers within SACE, I think that helps build a really strong support network. Uh, because there are going to be a lot of hard days, a lot of hard
A
days.
lot of hard days.
So,
A lot.
so maybe in the future I'll probably do like another video on kind of either a day in the life or just kind of describing what graduate life is like, because it seems like some of the people I've talked to even here, like for the undergrads, like they still have kind of a only generalization as to what graduate life is like.
Yeah, yeah,
So that might be interesting.
yeah. And
Uh,
everyone's experience is different. Like I know my experience is definitely different from your experience. Like no
yeah,
matter where you go, and even in the same program, different experience.
yeah,
Yeah, it's crazy.
yeah.
So
But yeah, I really appreciate you joining us.
yeah.
So if you want to learn more about his research, I'll try to link a few of his papers and some of the comments and description below, um, and definitely go look him up and some of the other research that's being done at
Go
NC
Wolfpack.
State.
NC State, go pack.
Oh, is that your mascot?
Yeah, yeah, Wolfpack.
Wolfpack.
Yeah.
Oh, we have the Sun Devil. So
Well, I mean, like, well, yeah, is it this or I want to do the wrong sign. Okay, like that. Yeah, yeah, there we go. Yeah,
yeah.
like that.
So
There we
ASU
go.
represent.
Hey,
Hey.
go pack.
But yeah, and this first kind of interview style video I'm trying out. So
Let us
and
know what you think.
yeah, let us
Yeah.
know and see if there are any other topics you want to talk about. Like smart textiles is one of them, but I know some people who are like
Hmm.
doing ocean engineering, some who are doing like biomedical engineering. So might be a good experience to like kind of take
Hmm.
a crack at interviewing those guys.
Yeah,
So
yeah.
no, thanks again, and I'll sign off. So keep calm and exit on.
Bye.
Bye.